I want to introduce now the time average Poynting vector. Unfortunately, I cannot deduce the Poynting vector as a subject in this lecture. I can only introduce it. So the time average Poynting vector is defined by this relation, and I want to deduce it now for the plane wave, its value for the plane wave. In the case of our plane wave, we have here the electric field as a phasor. It will be Ex naught, a constant, maybe a complex constant, times the exponential function minus j beta times z times Ex. So in this formulation I account for the vector I use vector notation, and of course we have also a magnetic field now in the phasor notation, which would be given by the magnetic field in the y direction times Ex minus j beta times z. But here we will have in the y direction, and of course this constant can also be rewritten like this is Ex naught divided by the field impedance Zf times the exponential function of minus j beta times z times Ey. So what we have to do is to get the cross product of these two elements. So the Poynting vector for the plane wave will be 1/2 the real part of the magnetic field, which will be Ex naught times exponential function minus j beta z times the magnetic field, but in the case of the magnetic field we have to take the conjugate complex, so it will be Ex naught divided by Zf. Of course Zf has a real value, but here we have to take the conjugate complex, and if I take the conjugate complex of this, then it will be exponential function of plus j beta times z. And of course you see we have to calculate the cross product Ex cross Ey. Of course this cross product will result in the z direction, and you see here we have Ex times the conjugate complex of Ex naught. This will be the absolute value, these two will cancel, and of course this is all real, and we will find for S the time average Poynting vector will be 1/2 Ex naught absolute value squared divided by the field impedance times Iz. So what I want to do now here in the next step is to have a look on the unit of S. So the unit of S, of course, will be equal to the unit of the electric field. I don't need vector notation here. The unit of the electric field times the unit of the magnetic field, and this will be volt over meter times ampere over meter, which is watt over meter squared. This shows us that the Poynting vector will describe the power which a plane wave will transport into the y direction, into the z direction. So again, we see here s, I will write it's 1/2 the absolute value Ex naught square divided by the field impedance times Ez. This again shows us that our plane wave described by these two equations will result in a power density which will propagate in the z direction, or on the other hand I can say a plane wave will transport a certain power density in the direction of its propagation, and this direction is now given by the z direction in our case. So I again have written here the so-called time average Poynting vector for a plane wave, and we will see that according to this equation a plane wave will transport a certain fixed power density in the z direction. Of course, this power density can be described by the electric field, or it can also be rewritten for the magnetic field amplitude. These are in principle the field amplitude. And to give you a picture for this, I will draw now here a right-handed coordinate system. So in this direction I will assume to have the x direction, in this direction I assume to have the z direction, and in this direction we will have the y direction. So, and we know in our plane waves the electric field has only an x component, so the electric field lines will point into the x direction. I can sketch this field lines. These are the field lines which would point in the x direction, though this is in principle the direction of the electric field, and we have the magnetic field points in the y direction, and so they are perpendicular to the field lines of the electric field. This would then be the magnetic field lines, and of course you see here these both fields define a plane in space, and in every point in this space a certain amount of power is transported in the z direction. So you see here, of course, these vectors should have the same length in principle, and this describes now the power density which is transported by the plane wave in the direction of propagation. And I will, in the next slide or in the next section, I will give you a model of this again. The model shows a plane wave which we introduced for the special case. It propagates in the z direction. The electric field lines are directed in the x direction, while the magnetic field lines point in the y direction. Clearly are shown the planes of constant field strength, ones in the positive direction and in the negative direction. I will show this now in a little bit more detail. In principle, in free space is no direction exist with a special purpose. All directions are equivalent, so a plane wave is able to propagate in any direction as we deduced in the general case. This we will show in a later step. The plane wave forms a unity. For demonstration, I will move the plane wave as a whole. This means it is easy to see that the plane wave can propagate in any direction in space. In the general theory, the direction is described by the wave vector. Also, the polarization of the plane wave can change, which means the direction of the electric and magnetic field will change in space. This we must account for when we study the reflection of a plane wave at the boundary of different dielectrics. With the help of the model, I try to explain that a plane wave can propagate in an arbitrary direction in space. So we started our considerations that a plane wave would propagate in the z direction, and what we can introduce now is a so-called wave vector, which will describe the direction of propagation. So in a different coordinate system, of course, this can have any direction, or in our original coordinate system it has the z direction. And if I draw here the x direction and the y direction, then we of course E and H, or the electric field and the magnetic field, form a plane of constant phase, and the k vector will be perpendicular to these three vectors. So if I want to formulate now wave propagation in a general direction k, I must introduce here k times the dot product of r. Here will occur the dot product, and what I have to choose is I have to choose the direction of the electric field to be perpendicular to the k vector. So this will be then a general formulation of the electric field which propagates in the k direction in space. And if I formulate the same for the electric field, then I know that formulated for the magnetic field, then I know the magnetic field will always be perpendicular to the E field and also be perpendicular to the direction of propagation. So this will be the formula for the magnetic field of an arbitrary wave, and here we again have the wave vector, the field impedance, which is Z0 divided by epsilon r. And of course this equation now will result in the fact that the unit vector of the electric field will be perpendicular to the k field, and it will also be perpendicular to the direction of the magnetic field. So both fields, they form, or the plane wave forms a so-called TEM wave. This means transversal electromagnetic wave.